Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin. I'm going to cover U-substitution today. So if g is continuous, whose range is I, and f is continuous on I, then the integral of f composed with g times g prime of x dx ends up being equal to the integral of f of u du. So we need to make sure that, that this function is continuous so that it is integrable. That's why we say this stuff up here. And how do we go from something that looks really messy into something that looks, relatively simple? So the way we do this is we have to find the function that I'm composing with. So the composed function happens to be your g of x. Now this is going to help you take your function of x and turn it into a function of u. But if I'm going to integrate it, I need to integrate this function of x with respect to x. So that means I need to integrate this function of u with respect to u. So this will help you change, again, the x's into u's, but I also have to change my dx's into du's. And we do that through, its derivative. So du dx. So we change it with its derivative. So du dx is going to be equal to g prime of x. Now, I need its differential, not its derivative, so I'm going to take this dx and put it to the other side. So du is going to be equal to g prime of x dx. And now you can see where the substitution is happening. So your composed function g of x turns into your u, and then your g prime of x dx ends up becoming your du. Now notice that there is a function that's still conserved here. That f is still conserved, so we're still going to have to integrate f. So let me show you this with an example. So first I want to find the function I'm composing, and I can see that the function that's being composed is going to be equal to this x squared minus 7. So I am struggle busing. So I have to find the function that is being composed. So the function that the composed function happens to be equal to this. So I have to find the function that is that we're using for the composition. So this x squared minus 7 is the function that's being composed. So this is x squared. God. So I'm going to do this using an example. I need to find the function inside the function. So we're composing g of x into f of x. So I can see that this is the inside function, is x squared minus 7. So we're going to call that our u. Now remember, I need my du as well because I need to not just change the x's into u's, I have to change the dx's into du's. So du is going to be equal to the derivative of this x squared minus 7, or 2x, followed by dx. Notice the beauty of this u substitution is that I also have this, this derivative in here, that I have this 2x dx. Now I'm going to rewrite this so it looks, identical to the definition up here. So this is going to be equal to the integral of the green function, which is the sine function. And then we have our u, which is this x squared minus 7. And then we have our 2x dx. Now we can see it looks exactly like this, that the integral, the f function, the function I'm still going to have to integrate is the sine function. And then we have our u, which is our g of x, and then we have our g prime of x dx. That means I can rewrite this as, well, f of u du. So this is going to be equal to the integral. Well, the f is still conserved, and that's going to be our sine function here. And then your x squared minus 7 ends up being your u. And then your 2x dx ends up being your du. So I've taken something that looks really messy and really turned it into something that's integrable, something that's a lot easier. So we have to integrate that sine function, which is going to be minus the cosine of that, of that of that u plus c. I'm leaving parentheses in here. They're not really required. So your last step in your u substitution is to unsubstitute. So remember that your g of x, or your u, ends up being this. So I'm going to unsubstitute that u, and we're going to be done. So this is going to be minus the cosine of u, which is x squared minus 7. All right, so let's do a couple more examples, and then get really used to this. So we're going to evaluate these two functions. I need to find really the function that that's being composed. So I have a function inside of a function here, and what we're trying to do is we're trying to find a u that also has, a du in here. It's kind of its derivative. So what I can see is that the square root is being composed with this x, 4 minus x cubed. So 4 minus x cubed. And what we notice is when I do my du, the derivative of this thing, or the differential of this thing, I'm going to get a negative 3x squared dx. Now, so notice that I have an x squared dx, not a negative 3x squared dx, but remember, these are equations, so I can manipulate them by, multiplying both sides by a constant. So minus 1/3 du is going to be equal to x squared dx. So now notice that I do have, this x squared dx in this expression, your x squared dx. So now we can make our substitution. So this is going to be minus 1/3 du. So what's still conserved? What's the f function? Well, notice what's still green is this division and this radical on the bottom. So this is going to be equal to the integral, the division, the radical still there. And I have this negative 1/3. Sometimes they put the du's in the top. I prefer not to. Just my personal preference. I like to see the integrand separated from the operation. So, and your u is going to be equal to this 4 minus x cubed, which is in the bottom. So this, simplifies this, which looks a lot easier. So let's rewrite this. We know that we can pull out constants. And this is going to be the integral of, well, I have a square root on the bottom, so this is u to the minus 1/2 du, and then we can use the inverse power rule. So this is going to be equal to negative 1/3 times, we have add 1 to the power, and then we divide by that, plus c. So divided by 1/2 is the same thing as multiplying by 2. So this is going to be minus 2/3. Now, u to the 1/2 is really just a square root. And this is going to be your u, which means I'm going to unsubstitute, which is your 4 minus x cubed, and then plus c. Now, this one might not look like a substitution, but it's one of my favorite to give because you have to rewrite it in order to see the substitution. So the tangent is built from the sine and cosine. So this is the sine of x over the cosine of x dx. Now, we're really looking for a function whose derivative is also in there, and I'm going to do a mistake on purpose. A lot of times people might say, well, what if I use the sine function? Because I know the derivative of the sine is the cosine. So if you do the sine function, then you know that its differential is going to be the cosine of function. So cosine of x dx. Now, I don't actually have a cosine of x dx. What I have is I have a denominator of the cosine, and right now this is cosine over 1. So this is not that substitution. I can't do it that way. So when I take this thing's derivative, I actually get a numerator here. So I chose poorly. That's kind of the idea. Now, sometimes you're going to do that. You're going to choose something that might not work, so then choose the other thing. So u is going to be equal to the cosine function. A lot of times when you have a rational function, the u that you're choosing tends to be in the denominator. More often than not, it's not always true. I'll do an example to where it isn't true. And it mostly happens to do with things that when you take the derivative, you get a denominator, stuff like logarithms. So, or tangent inverses. Let's make our substitution. We know that your u is that cosine function, which is on the bottom, cosine of x. And then you know that your du, well, actually, I have a sine of x dx, not a negative sine of x dx. So if I'm going to have my sine of x dx, I need to isolate that by multiplying both sides by negative 1. There we go. I have my sine of x dx. So this is going to be, negative du or negative 1 du. And we know that we can pull constants out like we did before, so we can say that this is negative the integral of, well, the sine of x dx is going to be your negative du. And then your, well, what's still conserved? What part of the function is still conserved? Well, I can see that this denominator is still here, so this is still a division. And then we have that negative 1 du. And I should have actually put that in orange. And then your cosine of x is going to be your u. Now, when I take this thing's antiderivative, we know this is going to be negative the natural log of the absolute value of u plus c. And now we unsubstitute, and we'll have our answer. So this is finally going to be minus the natural log of the absolute value of the cosine of x. Let's see. Let's do a couple more. All right, so let's evaluate these two integrals. So what I need to do is figure out a u so that its derivative is also in there. And in this case, remember I said that a lot of times it ends up being the denominator, except when you have a function that introduces a denominator when you take its derivative. So I chose the natural log function on purpose because this is comes up a lot. So what's the derivative or the differential of u? Well, this is going to be the derivative of the natural log of x, which is 1 over x, followed by dx. So now what I can see is that I have a 1 over x right here, dx. And, of course, I have that u. That's why I chose it. So this is going to be your u here. Now, it's kind of your choice. You can pull out the 2, or I can just double this, which does exactly the same thing. So you can say 2 du is equal to 2 over x dx. Regardless, this 2 is coming out. So now I can rewrite this. Let's pull out that 2. And what is still conserved here? Well, notice there's really nothing green left except, that 2 du. There's nothing left here. So your natural log is just your u function. So this is going to be u. And then your 2 over x dx ends up being your du. And what's the integral of u? Well, this is u to the, to the 1. So this is going to be equal to u squared. This 2 up front over 2. I'm just going to leave it like that. So this is going to be times 2 plus c. These 2's will cancel. So this is going to be equal to u squared plus c, where u is the natural log of x. We're done. Okay, so we're used to manipulating this right-hand side. What I want to do is I want to show you that you can actually manipulate both sides. And this is like a really nice example for that. So again, we're going to go after the composed function. So this x cubed minus 4. Now, when I look at my du, this is going to be equal to 3x squared dx. Notice that I don't have that. I have my u, which is, x cubed minus 4. Looks like the green's still going to be that 7th power, but I have an x to the 5th dx. So how do we pull that off? Well, notice that that this has a, well, let's rewrite this. Maybe you'll be able to spot this in a second here. So x to the 5th is actually built from these two powers, that this is, x cubed times x squared times this x cubed minus 4 to the 7th dx. So what I'm going to do is, let's color these up. So this is going to be x squared dx, which I don't need. Actually, I have a 3x squared. So we're going to go 1. Should give myself more room. 1/3 du is going to be equal to x squared dx. So that's good. Now, this pink is still good, or this purple is going to be your x cubed minus 4. Notice I have left this green function, this x cubed, but I have an x cubed right here, which means I can subtract 4 to both sides. So I can say u minus 4 is equal to x cubed. So I can actually write this in really this purple expression as well. So this is going to be equal to the integral. Well, x cubed is u minus 4. Now it's going to be times this expression, so we have to be a little careful here that, the green expression is still this. But this thing has to multiply by this, not just the 4 or the negative 4, but the entire expression. So we're going to need a parentheses row. And this is going to be just your u. And then your x squared dx is going to be 1/3 du. So let's pull out that constant, 1/3 du. Okay. Now, what makes this nicer is I had a monomial multiplied by a binomial to a power. Now what I have is a binomial multiplied by a monomial to a power. So this is nothing more than just u to the 7th. So I can distribute now because there's no exponent on this binomial now. So now I can distribute. I can't do this because that 7 really protects that binomial is kind of the idea. So I'm distributing this to both. What I'm going to have is 1/3 the integral of u. Well, this is 1 plus 7 is 8 minus 4 u to the 7th du, and these are integrable. So this is going to be equal to 1/3 times u to the 9 over 9 minus 4u to the 8th over 8 plus c, and then unsubstituting and simplifying, this is going to be equal to, I think I can make it, 1/3 times u to the 9th, u being this binomial, so x to the 4th minus 4 over 9. Really trying my darndest to squish this in here. To the 8 over 8. I'm going to simplify 4 over 8 is 2 on the bottom. Plus c, where your u is this purple expression. So I have x to the 4th, x cubed minus 4 here, and also x cubed minus 4 here. Of course, you can distribute this 1/3, so this turned into a 27, this will turn into a 6, and that would be it. So if you liked the video, please subscribe, and thanks for watching.